Some of the notation things in calculus that we have difficulty with is that we're introducing new symbols that we don't always use. For example, I have equals, I have approaches, I have implies. These are three connective symbols that are not used in the same context and mean three completely different things. And absolutely, they are not interchangeable. That would be the equivalent of interchanging letters of the alphabet to spell a word. You wouldn't get the same word. This is put between things to indicate exactness. So I might have something like, say, at the very end of the problem, x equals 4. This is only used in a limit context. So I would say the limit as x approaches 4 of a function. That's where I would use that one. And this one is an implication symbol, which is used between statements. Numbers do not imply numbers. That has no meaning. So I would say, if 4x equals 8, then x equals 2. That's equivalent to 4x equals 8 implies that x equals 2. Statement implies statement. I'm not saying numbers are equal. These are three completely different meanings of a symbol, yet what I notice on the quizzes is some of you go, oh, I just like to use it. That's just the way I do math. That'd be like saying, well, this is the way I make my zeros, Well, no, you don't get to invent the meaning of a symbol that has only one meaning. You got to get the meaning correct. So we want to get our notation straight. I had quizzes where some people I had one quiz, I counted 37 uses of an arrow on one quiz. There's only 5 problems. They used an arrow 37 times. None of them connected with the limit. They used the arrow as an equal. Now remember, arrow means approaches never reaches. So if you're writing 3 plus 4, understand what this statement means. This says that 3 plus 4 is not equal to 7. This is equivalent to putting a not equal. It says 3 plus 4 gets really close to 7, but is never equal to 7. I don't think that's true mathematically. So I don't think you want to use an arrow there. I think you want to use an equal sign. Now, another thing we're having trouble with is something called an operator. Now, this might sound very abstract, but this is stuff you've probably dealt with before. We know what functions are, but operators are a little bit different. We use them in kind of the same context. If I said the square root equals 5, or if I said the natural log equals 1.7, or if I said the sine equals 0. Mute yourself, please.
That's no, I'll be here.
Please mute yourself right now, please. You got to know if you're muted. Okay, can't compete. You're significantly louder than I am, which is unusual. All right, if I keep going, the limit as x approaches 5 equals 8. I have 4 absolutely absurd statements on the board here, and some of us are guilty of doing things like that. You see, the square root, you would say, is a function. Well, actually, more specifically, it's an operator. It requires an argument. Natural log of something, the sine of something, the limit of something. None of these has any meaning unless I insert something here. That's called the argument, what I'm inserting there. And so be careful that you're not saying things like the limit as x approaches 5 equal of what? It has to be of something. All of these I have to have of something, because that's what makes it an operator. So if you were using your calculator and you wanted to calculate something and you entered any form of a function, could be the square root function or the sine function, the calculator is immediately going to put an open parenthesis waiting for you to input something and then close the parenthesis. If you hit equals without entering something, the calculator is going to say you have an error because you asked an absurd question. So that's a minor thing, but I notice that especially with limits, a lot of people will say the limit equals, but it's not the limit of something. They'll just say the word limit equals. That'd be like saying the empty square root symbol equals. That doesn't make sense. Now, the last thing I want to make sure is when we're putting equal signs between things, making sure that those things are in fact equal. So here's a common error in calculus. I'm going to give you a simple example. If I said f of x equals x squared, here's a function. We're all familiar with this. Now, I want to evaluate this function, let's say at x equal 3. Now, there's a couple of ways I can say this. The formal mathematical way, believe it or not, is to write it like this. Vertical bar subscript x equal 3. Whenever you use this type of notation, this means evaluated at. A more convenient way would be to say f of 3. I think we all agree that that's a little bit simpler, and we would all agree that f of 3 is 9. Then would it be the case that f of x equals 9? If f of x equals x squared and I want to evaluate it at 3, then is f of x equal to 9? Absolutely not. Not even close. This is a parabola. This is a horizontal line. I am saying that my function equals 9 for all input. No. It's only equal to 9 for that input. I cannot equate these two. Mathematically, that is an egregious error. That's called a gross mathematical error. That doesn't mean ooh, disgusting. That means astronomically large. Yet we make this type of mistake all the time in math. F of x is not equal to 9. F of 3 equals 9. F of x equals x squared. F of x is a function. It cannot be equated with a scalar because now I'm saying it's equal to that scalar for all values of x. So when we're doing a limit problem, I'm going to need to get a wet paper towel in a minute. This is getting kind of icky. If I'm doing a limit problem, I'll keep it really simple. If I said I have the limit as x approaches 3 of, let's say, x squared minus 9 over x squared minus x, minus 6. I'll do something really simple like that. Now, the first thing I always want to do is ask, can I evaluate this directly? Can I do that? Well, if I try to evaluate this directly, I'm going to find that numerator and denominator both tend to 0. So I get that particular indeterminate form. So I also recognize, that means I can factor and cancel. So the top is x plus 3, x minus 3. The bottom is x plus 2, x minus 3. And then that equals, after I cancel, x plus 3 over x plus 2. And then, of course, that equals 6 over 5. Now, I have made a series of egregious errors. Oh, this is so wrong. I can't get any wronger mathematically unless I just make up the numbers. Yet a lot of us are doing this on our limits. And some of you are asking, I don't see a single error. The limit of this quantity is a scalar. The answer to this problem is a number. I just said the answer to this problem equals this function. Then I just said this function equals this number. There is no real number that exists where this quantity is ever equal to 6/5 because I have a removable discontinuity when x is 3. I can never actually evaluate this at 3. 3 is not in the domain of this, therefore plugging 3 into the function is an actual impossible statement. I've got scalar equals function equals scalar. That's absolutely impossible. It's utterly absurd. I am now saying that this quotient is equal to 6/5 for all real numbers because I put an equal sign between them. The error in the problem is I never took a single limit anywhere in the problem, but I gave a numerical answer that was equal to a function. And this, by the way, there is no x value where this is ever equal to 6/5. Again, that's where the removable discontinuity was. So how do I fix this? The limit of this is equal to the limit of this, and the limit of this is 6/5. The function is not 6/5. The function is never equal to 6/5. That's not in the realm of possibility because there's a removable discontinuity. There's a hole there. Oh, but the limit is equal to the limit, and now I can evaluate. Without that limit, there's no part of this that's correct, but I got the right final answer. No, actually you didn't, because you said the answer was this, and it's definitely not this, and this isn't equal to this. And a number of years ago, I had a student in calculus, and it was hysterical. To every limit question, he would write 0, comma, infinity, comma, 1, comma, D and E. Because he noticed in the homework that almost every single answer was one of those 4. So he'd write that to every limit problem. He'd write 0, infinity, and D and E. That was the best part. And often one of those was the correct answer. And so he'd always argue, but I have the right answer. And I'd always remind him that's equivalent to on the multiple choice test filling in all of the bubbles. But I have the right answer. Yeah, but you also have multiple wrong answers. So no, it doesn't work that way. Now,
So,
yes.
in this particular instance here, where you're going, you're kind of writing things vertically, like one under the other. What happens in like a test where there's perhaps not a lot of room? We want to move horizontally the way that we're progressing the
Write
problem.
your equals horizontally. I think most people, when they're doing algebra, for some reason, this is neither right nor wrong. Most people, when they're doing algebra, like to work vertically. Working left to right, part of it is always the space issue. You know, if you have a long statement and you're moving left to right, you may not be able to fit everything. But like, you know, if you have a long statement, it's really about readability. I could write this. Well, see, I don't have the room though. But sometimes I'll put extra things up here. That left and right vertical is really not important as long as it's clear. I'm saying this quantity equals this quantity. I could have put this right here. On my keys, I'll often put 2 or 3 things and then the next line. You know, it's a space. That's all it is, a space issue. Now,
So you got,
excuse me.
So you got all the way to the bottom, and you're like here now. So you ran out of board length, and then you wanted to continue up to the top. It would be wrong to then draw like an arrow that went all the way up.
I see what you mean. I'm not a big fan of that. And, you know, I see what you're saying. He's saying, okay, now I want to keep going and I'm going to take you over in this direction. Yeah, I don't see a problem with that. Sometimes that's just like, I didn't leave myself enough room to begin. When I'm working on this board, I will sometimes do that because I don't want to erase everything that preceded it. I want it to still be there and for you to read it. And I say, now I'm going to continue the problem over here. It's kind of old fashioned, but you know what? If it's clear, if there's no way somebody can misinterpret your attempt, or you know what I'm saying? If there's no possibility of misinterpretation, then that's fine.
Well, excuse me. So can you just put, we're putting just an arrow to the 6/5 because we're not saying the everything's equal to the 6/5. We're in with the limits, right?
This would be incorrect. This would be correct.
So what would we put that then?
Quantities approach limits equal. And that's, by the way, that's an important question, Nathan. I recognize the voice. It's quantity. This X is approaching 3. So therefore my limit is 6/5 because that's where the hole is. Now, here's another, what if I wrote this? I'm going to put the word limit in front of this. It turns out this is actually an error. You say, well, why is that an error? Remember what we're saying here. We're saying that this quantity algebraically is identically equal to this quantity algebraically, except potentially at 3. Then we're saying this quantity algebraically is identically equal to this quantity algebraically, except potentially at 3. And by the way, that is a true statement. But if I write limit, then I'm saying this quantity algebraically is identically equal to this quantity algebraically. This quantity is not equal to this quantity. The limit of this quantity is equal to this quantity. That's going back to my f of x equals x squared, therefore f of x equals 9. No. This quantity is not 6/5. The limit as x approaches 3 of this quantity is 6/5. I don't write the limit because if I write the limit, then I'm saying these quantities are identical and I still haven't answered the question. The answer to the question should no longer have a limit. Now, this is the first quiz on limits. Oh my gosh, notation typically is just horrible on the first couple quizzes as people are learning the process. Don't beat yourself up over that. We just basically, it's like you have a big picture idea, you're writing this tremendous essay, but you're misspelling a lot of the words. I'm trying to get you to spell the words correctly because I love what you're saying in your essay. But if you spell enough words incorrectly, no one's going to figure out what you're saying because they can't get past the misspelled words. This would be a misspelled word if I throw the limit in there. This is not life and death, but we do want to fix it. So what I have here is exactly the entire problem from beginning to end. No part of this should change. That this is the answer. That's
So when we're writing for the answers, so we just the equals, then whatever the limit is, or box around it, that's fine for when you're looking at it? Or do you actually want us to like re-summarize, like the limit of 3 of this function is equal to this as the limit?
Oh,
like
you
for the
like
final
bring it
answer?
back up to here?
Yeah,
Oh,
like
you
kind
know
of like
what?
summarizing.
I have no problem with that. A lot of people do that. And here's a really good way to think of this. You're working for somebody. You've been given some project and you've got something you got to do, and you're doing all this stuff and you're doing all the math and you got the answer, but you're doing the work for somebody else's eyes. So you want that person to interpret your work exactly correctly. So you say, you know what, I'm going to do exactly that. I'm going to say, here's the problem. I did all my work. Now here's the summary of my answer. So what Nathan's saying is, at some point, would it be okay to now say, this is equal to 6/5? Absolutely. I don't need you to do that, because the process here makes it very clear, right, that this is the answer to the question. But restating it is always nice. I had several people do that on their quizzes. They did perfect work and then restated it at the end, because sometimes the problem can be really long and we can actually kind of get lost in the process. Or like William said, you know, I got to finish it somewhere else. It's so busy that maybe restating it at the end. It is never incorrect to restate that is equal to that, because you've justified every step of the way. But I think most people, when they see this, I think it's pretty clear they're saying, yeah, that's my final result. So from a notation standpoint, if you're doing it correctly, you understand it, I want you to also say it in such a way that anybody reading it is going to interpret it exactly the way it's supposed to be. If I'm missing things, if I'm saying this without the word limit, then actually none of it is true. And I'll give you a simple example of something we did last day.
Wait, can I just ask a quick question?
Sure.
You did the arrow to the 0 over 0. Is that okay?
That's
all the time.
Well, did you notice that how I wrote it? I wrote it within the brackets. That's kind of universal notation to say the form of the problem is the 0 over 0 form. And if you have a 0 over 0 form and it's algebraic in nature, polynomials, then it means I'm probably going to be able to factor and cancel. But remember, we also had trig stuff. Now I want to make sure everybody understands. Last day we proved this. I'll use X. We proved this. That was a very powerful result. But that limit is kind of important, because if I ever said this, there is no value of X that is ever true. Sine X over X is never equal to 1. In fact, the only time sine X and X are ever equal is when X is 0, which is not going to work. The limit is 1. The quotient is never 1. And again, if I drop the limit, then I'm saying something that's very untrue. Sine X over X is most definitely not equal to 1, but the limit is, and that's really important. Hang on a minute. I'm going to grab a paper towel here. My board is getting increasingly harder to erase because I got all this ink built up on it.
I got a question about the notation, Professor.
Yes.
I feel like I may have grossly misused the implication symbol in my statements.
You probably did. Yeah, people, for whatever reason, because in prior classes nobody pointed it out, but people like to use implications instead of equals, but an implication means something else. So simple rule of thumb, if you're equating two things, just use an equal sign. The implication symbol, remember, it means if A, then B. If statement A is true, then statement B is true. Statement A implies statement B. That's what an implication symbol is. It's for logic, what's called a conditional statement. Putting it in an algebraic process is not really logical, because that's not what it means. When we wrote the epsilon delta,
I misunderstood it.
Yes,
I thought that it.
Oh, sorry.
I thought that it meant that the work wasn't that it didn't have to be included, and that the implication was that you understood that the work had been done. So I was hiding work through the implication.
An implication symbol, when you're doing work, would say, you know what, algebraically, this is low level stuff. You don't really need me to explain that you just use commutativity of addition. You know what I mean? Yeah. So you're saying the truth of this statement implies the truth of this statement, but you wouldn't say 3 plus 4 implies 7. That makes no sense whatsoever. 3 plus 4 doesn't imply anything. If I said 3x equals 7, that would imply that x equals 7/3. That would be an implication symbol. The truth of one statement guarantees the truth of another statement. So a statement might be an entire equation, you see. A statement might be words. If we score more points, then we will win the game. Scoring more points implies winning the game. That's an implication. Okay, so let's continue. Let's move on. We're going to look at what are called infinite limits today. And so I'm going to introduce you to a couple of things that you may or may not be familiar with and some vocab. So I'm going to break out my graphing calculator for a moment. Now, I want you to consider, I'm going to establish a rule, and we're going to actually treat this as an identity. I want to consider the limit as x approaches infinity, yikes, of 1 over x. Okay, so what I've done is I've put it on my graphing calculator. Hopefully you can all see this. Okay, it's easier than going back and forth between Desmos. That just takes too much effort. So
Yeah, we can see the graph. Sorry.
can you all see the graph? There's it's just a simple graph. Now, as x grows without bound, and this is a term you're going to hear me use all the time, without bound. Without bound means unbounded. It means it's getting infinitely large, or negatively infinitely large. As x approaches infinity, as x grows without bound, what is happening to the quotient? So if x is astronomically large, then its reciprocal, we'd say, is infinitesimally small. Okay, that makes sense. But going back to the picture, you notice that the x-axis acts as a horizontal asymptote. This is getting closer and closer and closer to the x-axis. So I just simply drew it.
You're starting to lag, sir.
Oh, hold on.
Yeah,
Oh,
you're starting to lag.
give me 1 sec. I just saw that thing. Hold on, internet connection. Why would my internet connection be unstable? Are we okay right now?
For right now, yeah.
Oh dear, that's not good. I'm not given a choice at the bottom to, oh boy. All right, well, I'm looking at this going, I don't have any place on the bottom here where I can change my Wi-Fi. That may be the problem. Like I said, this is a new computer and we have very powerful Wi-Fi. Okay, so everybody sees this is an asymptote. Now, does the curve ever hit the axis? No, there is no value of x where I ever hit the axis. But as x gets bigger and bigger and bigger, the y is getting smaller and smaller and smaller. So the limit is 0. This is another way of saying I have a horizontal asymptote for the x-axis. It's getting closer and closer. And in my graphing calculator, like I said, I love using this. It appears that my graph is disappearing into the axis. No, it's not disappearing into the axis. What's happening is the distance from my graph to the axis is getting less and less and less and less and less. It's approaching 0, it never reaches 0, but the limit is 0. This I want you to forevermore treat as an identity. And that's a really, really powerful statement right there. And this is what we're calling asymptotic behavior or asymptotic convergence. A significant amount of calculus is based on this concept. If you've ever had statistics, all of statistics is based on what's called asymptotic behavior or asymptotic convergence. You see, if I'm taking samples to make conclusions about a population, assume the population is infinite, in fact. You know, I could be talking about water molecules on planet Earth. It's not infinite, but it's so big I can't count it. As my sample gets bigger and bigger and bigger and bigger and bigger, my sample results start looking more and more like what the population would be. Okay, there's a limit there, and it's called, again, asymptotic convergence. So with this statement here, I am interested then in how can I use this in general? So let's consider the following. Let's consider f of x is x to the 4th minus x squared plus 1 over x squared minus 1. Now, if you look at this function, there's a couple of places, you know, x equal plus or minus 1 primarily, where this is going to be undefined as a quotient. And graphically, what that means is I'm going to have vertical asymptotes. So I'm going to graph this for you in just a second here. Let me get in better light here. So hold on one moment. I have to change out of the last one. Next to fourth. Okay, here we go. And now let me do my window. I'm going to make my window -10 to 10 in both directions. By the way, the window you use is very, very important in general. Okay. Hold on. There we go. So hopefully you can all see this. Can everybody see this?
There's a little bit of a glare.
How about now?
A little bit better. Yeah.
It's a crazy graph.
Right.
It's a crazy graph. So I'm going to show you what it looks like on here. It basically looks like this. Okay. I mean, it's a cool graph, but it's a crazy graph. I got 3 portions of the graph. I have vertical asymptotes. It's going crazy again. Hopefully, everyone can see that a little bit. It's going crazy in each direction. Okay, great. So why am I showing you this? Well, because this is like one of the coolest parts of calculus to me, what we're about to do. So you're looking at your graph, but I'd like you to back up. I'd like you to stand back. In fact, I'd like you to keep backing up. I'd like you to back up. Kind of like in the Men in Black, you know, we're going to go LSAT 5,000, or I don't know, whatever it is. You know, I'm going to go into outer space. I'm going to go into a satellite, and I'm going to get really far away from this. So in other words, I'm going to zoom out. So all I'm going to do right now is change the window slightly. Right now, my window is -10 to 10 in both directions. I'm going to make my window -100 to 100. That's not that big. Okay, I'm going to make my X window -100 to 100. Now I'm going to make my Y window -10 to 10,000. All right. Anybody see anything interesting?
Just the left and the right. It looks like an X squared, like a really wide one, but I'm assuming it's not.
Yeah, it looks
The reason
like
it looks wide is because I've made X go from -100 to 100 and Y go from up to 10,000, so I could fit it all on there. Nathan hit it right on the button. Doesn't that just look like Y = X squared? Can everybody see that? All I did, wait a minute. My original graph was -10 to 10. I just went -100 to 100. How come it looks like Y = X squared? Why did the picture of this graph, when I zoomed out, completely change? It now looks like by the way, it looks like a perfect parabola. Well, let's go back to here for a moment. If I do the long division on this, it turns out this is equal to X squared plus 1 over X squared minus 1. If you just simply do the long division, and by the way, if you put this over a common denominator, you'll see. So this is my graph. As X gets bigger and bigger and bigger, you see this part here? As X is getting bigger and bigger and bigger, that's getting smaller, isn't it? Because the X is in the denominator. So by the time X is 100 or 1,000, this is microscopic, which means it's really not even contributing anymore. This is what is called, and this is a vocab term, this is called a transient term. This is a very, very important concept. This is a transient term. A transient term, think of it as being kind of a non-contributor. In fact, the further I go away, the less it contributes, which means that after a little while, this graph thinks it's actually just X squared. Okay, and so the formal and correct mathematical notation that none of you have ever used probably in your entire lifetime in the proper context is By the way, this is the meaning of the squiggles. Most people don't learn this symbol correctly. They use the symbol completely incorrectly. Squiggle means asymptotic. It has no other meaning in any context. This graph is asymptotic to this graph. Meaning, if I put one graph on top of the other, remember the first one went all over the map? If I put y equal x squared on top of that and then I start zooming out, I won't be able to see the difference after a while. That's crazy. That's so my graph of y equal 1 over x is asymptotic to 0 because as x gets bigger and bigger and bigger, I close in. So the concept of this is called asymptotic convergence because the difference between these two graphs is this tiny quantity called a transient term. So if I have a transient term, then it's approaching 0. Now, I can't say, let's take the limit of this as x goes to infinity. Well, no, because then that would be going to infinity. But what's happening is this becomes a non-contributor. So this graph starts looking like this. Now, an asymptote is a line. You guys remember doing those with hyperbolas and things. An asymptote is a line. To be asymptotic just means you're closing in on something else. You're looking like something else. And a significant amount of calculus is based on this concept. So with that statement there, what we want to do is consider, we're going to very specifically consider rational functions right now. A rational function, remember, is a quotient of polynomials. So if I've got trig or other things in there, that's not rational. So I would like to consider the following. I'm going to do the limit as x approaches infinity. Let's say of 3x squared minus 6x over 5x cubed plus 4x plus 1. This is a rational function, okay? Because it's a quotient of polynomials. Now, x is growing without bound. So obviously, if x is growing without bound, just think of your parabola. If x is growing without bound, your y values are approaching infinity. Approaching infinity. You never reach infinity. Sort of like infinity minus 1, infinity. Okay, I'm there. No, you can't reach infinity. And infinite means it just goes forever and ever and ever and ever. My numerator clearly is approaching infinity. My denominator is clearly approaching infinity. Infinity over infinity is not a value. This is the form the limit will take. Just like when we did 0 over 0 as a form, infinity over infinity is a form. Again, it's called an indeterminate form. But if it's an infinity over infinity form, it will also tell me how I'm supposed to attack this thing. Okay, so when I look at that and go, okay, numerator and denominator are both growing without bound. So does that mean I have infinity over infinity? Let me cancel them and get 1. No, it doesn't work like that. But it does tell me there's things I can do. So very specifically, what I would like to do in this case here, look at the leading term in the denominator, x cubed. Only the denominator, don't look at the numerator. If I multiply numerator and denominator, I'm going to multiply numerator and denominator by 1 over x cubed, which is a legal move. You can never multiply or divide by something that can potentially be 0. X is not potentially 0. Remember, x is growing. What will this give me? Well, on top, it would give me 3 over x minus 6 over x squared. On the bottom, it would give me 5 plus 4 over x squared plus 1 over x cubed. Now, just for a moment, if I take away the word limit, is this quantity algebraically equal to this quantity? Yeah, for all real numbers except 0, they would be correct. They would be equal. Now, remember, the limit of a quotient is the quotient of the limits. The limit of a sum is the sum of the limits. So technically, I don't feel like rewriting it. I can move this limit to here, to here, to here, to here, to here. Meaning right now it's the limit of this minus the limit of this over the limit of this plus the limit of this plus the limit of this. That's how limits work. Again, the limit of a quotient is the quotient of the limits and the limit of a sum is the sum of the limits. So that limit moves in front of every single one of these terms. But we started by talking about the limit as x approaches infinity of 1 over x, and we said that limit is 0. That's 0. That limit would be 0. So we often write it like this. That term is approaching 0. 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 All of these are transient terms. My numerator, therefore, is approaching 0. My denominator is approaching 5. And what is 0 over 5? 0 over 5 is 0. So the limit is 0. Graphically speaking, that would mean that the x-axis once again acts as an asymptote. Okay? Now, everything I did is absolutely correct and valid, but there may have been an easier way to look at this. If you consider the degree, the numerator has a smaller degree than the denominator. And when I did all this algebra, my numerator approached 0 and my denominator did not. I can actually use the argument of degree, which we're going to do in the end of all this. I'm going to show you how to do that. But it's kind of cool. We just did an infinite limit and we got an answer. So again, graphically, it means that it's approaching the x-axis. It never actually hits the x-axis. It's just approaching. So now let's do another. So let's try another one. The limit as x approaches infinity of 6x to the 4th plus 3x over 2x squared plus 1. I'll keep the number of terms small just so I don't have to write as much. Now, like before, numerator and denominator are growing without bound. So we would say this has the form infinity over infinity. Infinity over infinity, it turns out, is one of our favorite forms because the algebra required to answer the question is a lot less than the algebra required to answer something of the form 0 over 0. Because 0 over 0 form means I probably have to factor and cancel and do a bunch of stuff. Infinity over infinity forms often mean I only really need to look at the degrees to make my conclusion. So like before, we'll look at the lead term in the denominator. So I'm going to multiply top and bottom by 1 over x squared. And when I do that, this will equal the limit as x goes to infinity of, on the bottom I'll have 2 plus 1 over x squared. On top I'll have 6x squared plus 3 over x. Now again, algebraically, that quantity is equal to that quantity, so therefore their limits are also the same. Now, as x grows without bound, once again, these transient terms both approach 0. Great. My denominator, therefore, is approaching 2. But what about my numerator? As x grows without bound, 6x squared also grows without bound. So my denominator, or excuse me, my numerator is approaching infinity. My denominator is approaching a constant and my numerator is approaching infinity. That means my limit is infinity. A limit can be infinity. Graphically, what does that mean? That means it's going like that, like y equal x squared did. It's growing without bound. Okay. Cool. All right, now let's do one more.
Yes, sir.
Yes.
On the previous question, it was they were both approaching 0 in the previous question, and there was a constant in the denominator, but that one, the answer was 0. Why?
Because the numerator approached 0. So here's by the way, the reason you're taking the lead term in the denominator is because you want to create a situation where your denominator approaches a non-zero constant. Then your numerator is either going to approach 0 or infinity or something else, and I can evaluate that limit. If my denominator doesn't approach a non-zero constant, I won't be able to do the overall limit. That's why we use the denominator. So in the first example, the degree of the numerator was smaller and I got a limit of 0. In the second example, the degree of the numerator was bigger and I got an infinite limit. Now let's do one where they're the same. So now I have a quotient of two third-degree polynomials, and I'd like to know what's happening as x grows without bound. So once again, the form is infinity over infinity. What if my denominator was growing without bound, but my numerator was constant? Well, then that limit would be 0 because it would be a transient term. What if my denominator was approaching a constant and my numerator was growing without bound? Then the limit would be infinite. This is an indeterminate form because they're both growing without bound. So now I'm going to multiply top and bottom by 1 over x cubed. When I do that, this will become 2 minus 6 over x on top, 3 plus 5 over x squared plus 7 over x cubed on the bottom. Now I have several transient terms, and this is why we love limits to infinity, because all the transient terms are no longer going to be contributing in any conceivable way. As x grows without bound, all of these terms are going to approach 0, and all I have left is a 2 and a 3. So that means my answer is 2/3. And do notice that 2 and 3 are the lead coefficients here. That's not a coincidence. Okay, so we've just come up with a scenario that we can now address 100% of the time. When you have a quotient of polynomials, and very specifically, they have to be polynomials. My exponents have to be positive integers. I can't have fractional exponents. I can't have roots. I can't have things like that. I can simply look at the degree to make the argument. So it's a beautiful thing. So let's write it this way. If I said, I have the limit as x goes to infinity of f of x over g of x, and let's say that f is of degree m and g is of degree n. Okay. I'm saying f and g are both polynomials with the following degree. Well, I have 3 possibilities, don't I? I have if m is less than n, if m is equal to n, if m is greater than n. So let's start. If the degree of the top is smaller than the degree of the bottom, then my limit is 0. If the degree of the top is greater than the degree of the bottom, then my limit is infinity. What if the degrees are the same? Then the answer, I'm going to write it in the form a over b. The answer would be the ratio of the lead coefficients. That's it. Boy, that's a really easy one if I recognize. Okay, so taking an infinite limit when it comes to quotients of polynomials is one of the simpler things we do in calculus, but it's also a very powerful thing.
Oh, before you erase it, if there's a square root in the function, is that like
not a rational function, and none of this applies.
okay?
Absolutely, this only applies if f and g are polynomials, period. Now, the question is, what if we have a square root? Hold that thought, because we're going to do that one. What I'm showing you only applies when it's a quotient of polynomials. The reason is there's no degree. Degree is defined as being the positive exponent that I see that's an integer exponent. So fractional exponents don't contribute to degree. So let's do a simple example. I want to do the limit as x goes to infinity of 6x cubed minus 4x squared plus 7 over 8x to the 4th plus 9x plus 1. And I don't feel like doing all the algebra. Can I just simply answer this question? Anybody want to try it? What do you think the answer is? Yell it out without doing any work.
6 over 0.
The answer is 0, but you're going to give your justification because you don't want it to look like a guess. And here's the justification. Degree of numerator less than degree of denominator. That is your justification, and that is totally acceptable to give that. In fact, what I did earlier by multiplying top and bottom by 1 over x to the 4th, that's the algebraic way of getting the answer. It's absolutely correct. But the lazy mathematician would say, you know, I'm going to get this result eventually because of the degree difference. The degree of the bottom is bigger, therefore my limit is 0, and this is my reason. I need to include that, otherwise, I haven't justified why that's the answer. This is it. And you should like this because it's, well, it's not very much work. It's pretty nice. Now, Nathan asked the question, what if I have something else? What if it's not polynomials? For example, what if I have a square root? Yikes. Then what do I do? Well, if I have a square root or something of that nature, we'll do an example of that. I can still use a lot of what we just did, but I have to be a little bit more clever. So let's say the question is this. I want you to find the limit as x goes to infinity of the square root of, how about 6x to the, I don't know, 8th power minus 4x squared plus 1 over, I don't know, let's say 3x to the 4th plus 3x squared. All right. Yikes. Well, I can't use degree as an argument because there's no degree on top. I have a square root of stuff. But I can still do algebra, and I'm going to show you the algebra. I'm going to show you the only algebra. Now, what's interesting is this question comes up in a lot of textbooks. I have never seen the explanation of how to find the answer in any of these textbooks. They'll throw the question, but they won't guide you how to get there. So we're going to do some scratch work off to the side. I'm going to take 6x to the 8th minus 4x squared plus 1, and I want you to factor out the x to the 8th. I want to factor that out. Well, how do I factor that out? Well, that's actually quite easy. What will that leave me with? 6 minus 4 over x to the 6th plus 1 over x to the 8th. Okay. I know that's correct because if I distribute, I'll get back. Now, why would I want to do such a thing? Because now the square root of a product is the product of the roots. So I have the square root of x to the 8th, which is x to the 4th, times 6 minus 4 over x to the 6th plus 1 over x to the 8th. Okay, so I'm going to put this right here. Now, what about the denominator? Can I do the same thing? Sure. Sure, I can factor the x to the 4th out of this. Let's do that. Let's factor x to the 4th out of this statement. And that would leave us with 3 plus 3 over x squared. Now, I know that's correct because if I distribute, I'll get the same thing. So I'm going to write that as yeah, okay, 3 plus 3 over x squared. I think I wrote that correctly. Now, if I drop the word limit, is this quotient equal to this quotient? Absolutely. Now, I can't evaluate this yet because I still have the indeterminate form of infinity over infinity. But what about those x to the 4ths? Well, I'm pretty sure I can cancel them right now. And now my numerator would be this. My denominator would be this. Now you see a lot of transient terms. Now remember, the limit of a quotient is the quotient of the limits. The limit of the root is the root of the limits. So again, I can pull the limit and put it in front of each one of these terms. And that means that that term would go to 0, that term would go to 0, that term would go to 0. And what would I be left with? After I take that limit, I would be left with the square root of 6 over 3. And there is my answer. So the question of what to do when it's not a quotient of polynomials, the same algebra we did to develop the quotient of polynomials. In other words, look at the degrees, manipulate them, cancel them, do whatever it takes. What I'm showing you is the path to do this problem. Now, this is a very, very advanced problem. In fact, on the next quiz, I think the quiz on this one, I put this one or one like this down as a bonus problem. Okay, so infinite limits are our friends. They're generally simple to work with. Now we're going to look at the evil type of infinite limits. The one that nobody likes, but still comes up. So I want to go back to the y equal 1 over x picture that we had earlier. Okay. If I'm considering, all right, f of x. Now we did this earlier. We said, well, I got this beautiful situation here. As x grows without bound, I know that I'm approaching the y-axis, and if x goes negatively, the x-axis, if x grows negatively without bound, same thing. But now the question is, what happens if x is approaching 0? Ooh, as x is approaching 0, what's happening? So there's two extremely important conclusions we want to reach here. I said the limit as x approaches 0 from the right of 1 over x. That's what the little plus sign means. I'm approaching 0 from the right. As x approaches 0 from the right, 1 over infinitesimally small value gives me astronomically large value. Okay. As x is getting smaller and smaller and smaller, its reciprocal is getting larger and larger and larger. And in fact, I can keep getting closer and closer and closer to 0. There's no smallest amount, so therefore I am unbounded on the way up. This limit is infinite. And I also have a vertical asymptote there. That's where vertical asymptotes generally come from limits that produced infinities like that. Now, what if I ask the question, the limit as x goes to 0 from the left of 1 over x? Now, again, as x approaches 0, 1 over x is growing without bound. It's getting astronomically large. But the difference is all of my x values are now negative because I'm approaching from the left of 0. So therefore, x is always negative. Therefore, its reciprocal is always negative. And so if I'm growing without bound negatively, then that limit would be negative infinity. These are, again, very, very important results. You cannot calculate these. And no manipulation by plugging numbers into a calculator would be very useful. You see, if I plug numbers into a calculator and I have a finite number on my screen, I really can't justify an answer of infinity. That's not where it comes from. So now here's the question. What if I just simply ask, what's the limit as x approaches 0? Anybody want to try this?
Does not exist.
Does not exist. Why?
Because the limit from the left does not match the limit from the right.
Beautiful. Okay. By the way, just so you guys know, I give out airline miles for good answers and good behavior. That's 100 miles. I'm giving you 100 miles. I give out airline miles throughout the course of the semester. They have no cash value and they're not redeemable, but everybody feels good when they accumulate airline miles, like on your credit card. So great answer, William. DNE, because the limit from the left is not equal to the limit from the right. Now, we're cheating because we have the graph. But the beautiful thing is everything I have to the right of the graph, we would have answered without the graph. I like doing the graph to illustrate what we just said. This is the mathematics. Here's the verification that everything we said was correct. But remember, you never need the graph to do the math. The graph just, again, illustrates what the math said. So these are called asymptotic types of limits because I'm going to the infinity. From an algebraic standpoint, this is probably the easiest type of limit to take because there's absolutely no number crunching whatsoever. But from a conceptual standpoint, this tends to give people the most trouble. Okay, for whatever reason, this just tends to give people the most trouble, this type of limit. So these types of questions most of the time end up being one-sided limit questions. So let's do an example because I want to walk you through the proper notation that I want you to get used to using. See, when we use the brackets to indicate something is of the form 0 over 0 or something is of the form infinity over infinity, that's the form. That's not the answer. The form tells me, therefore, the type of strategy I'm going to perform. These are non-indeterminate forms. They're way worse. So suppose I wanted to take the limit as x approaches 6 from the right, let's say of x minus, oops, not x minus, sorry. Just on the bottom, x minus 6, and on top, let's say, let's keep it simple, x minus 10. Let's keep it really simple. Now, is this an indeterminate form? No, it's not. An indeterminate form is when both numerator and denominator tend to 0 or both tend to infinity. Right now, clearly my denominator is tending towards 0 and my numerator is tending towards -4. Oh, that is so ugly. That is so ugly. Now, at first, people want to say, the limit is undefined. Problem is, a limit cannot be undefined. That's not an option for a limit. Remember, I mentioned this last time. A limit has only 3 possible answers: finite, infinite, D, and E. Undefined means you actually tried to divide by 0. You can't divide by 0. We're asking what's happening as I approach 6, not what's happening at 6. Oh, so now I need to go back. As x approaches 6 from the right, x minus 6 is approaching 0 from the right. And that little plus sign is the single most important part of my answer here. You see, I'm not just approaching the form -4 over 0. I'm approaching -4 over something approaching 0 from the right of 0. Now, if your denominator is approaching 0 and your numerator is not, that means your quotient is growing without bound. So that means automatically you know your answer is going to be infinite in nature. What you don't know, is it going to be positive infinity or negative infinity? And I don't need a graph to make that conclusion. So going back to the statement here, -4 over 0, right, is undefined. But my denominator is approaching 0, which means that quotient is growing without bound. Okay, mute yourself, guys. That
sorry, there was a question I wanted to ask. So extendingly, that means it's 0.1, 0.2, yada, 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 for in the denominator, right? All values of that?
I'm not sure I understood what you just said, but we'll come back to that. a little too fast. Okay, so my denominator is approaching 0, which means my quotient is growing without bound. Is it growing without bound positively or negatively? My numerator is negative and my denominator is approaching 0 positively, which means that quotient is negative. I'm growing without bound negatively. Now here's what you're going to like. Limit equals -infinity. I am done. There is absolutely nothing else I can write. There's nothing else I should write. Form, answer. I'm done. There is no algebra, there is no arithmetic, there's no using my calculator to try different values. Kind of missing the point if I'm doing that. When you have the asymptotic limit, the main thing is to determine which side are you on. Are you approaching positive infinity or are you approaching negative infinity? Now, how do I know that I have that type? Because my form said my denominator was approaching 0, but my numerator was not. Now, without the plus sign here, if I just said you're approaching 0 and you didn't know if it was right or left, then you could not evaluate that limit. There's missing information. So going back to the original statement, if that wasn't a plus sign, if I just said 6, then you would actually have to look at both the left and right limits and, like earlier, are they the same? Are they different? Yikes. I don't like that question. It's just really long. So let's do another one like of this nature, because I want you to get used to how to write the answer and actually how little you really have to do to give an excellent answer to the question. So let's take the limit as, how about x approaches 2 from the left of, let's say that's x minus 2 squared, and on top it's x plus 1. How's that? Okay. I'm approaching 2 from the left of 2, which means that x minus 2 would always be a negative value. So I'm going to determine the behavior And again, the reason we're going to determine the behavior is that tells us the strategy. Let's just say hypothetically that this was an infinity over infinity form. Then I would look for something particular. What if this was the 0 over 0 form? Then I would look for something else particularly. Okay, so we've got to make sure we understand. Right now, my numerator is approaching 3. And by the way, it doesn't matter if I'm approaching 3 from the right or from the left. It only matters if I'm approaching 0 from the right or from the left in a quotient. I'm approaching 3. Yes, technically I'm approaching 3 from the left, but it's still a positive number. That's all that matters. As x approaches 2 from the left of 2, that means x minus 2 is always negative. But now I'm squaring it. So I'm approaching 0, but from the right. Again, as I approach 2 from the left, x minus 2 is approaching 0 from the left, but I'm also squaring it, which means I'm approaching now 0 from the right. Positive numerator, quotient's growing without bound, denominator is always positive, so my limit is positive infinity. That's it.
Professor, why does the denominator being squared mean that it's being approached from the right?
When you square a real number, can you get a negative value?
No, you can't.
Yeah, that's why. Now, by the way, hold the thought. What if the square wasn't there? Then this would have been approaching 0 from the left. But because I squared it, the result was approaching 0 from the right. Because of
So if it was cubed,
now back to the left again.
okay. So if
that
it's like
that would be almost devious putting a cube on there. I would never think to do that. But you're absolutely correct. If I put an exponent on there, you've got to say, okay, how does the exponent affect this? Because it may or it may not. In this case, it definitely affected it. So now let's do one more set of examples, because we've looked at several different types of limit problems thus far, and I want to make sure that we're all on the same page here. So let's suppose I have the limit as x approaches, I'm going to keep this really simple. The limit as x approaches, let's say, find something that's not too terrible. Limit as x approaches 3 of x minus 3 over x squared minus 9. The limit as x approaches infinity of x minus 3 over x squared minus 9. The limit as x approaches negative 3 from the right of x minus 3 x squared minus 9. So I gave you the exact same function in all 3 cases, but I asked you for 3 different limits. I am most definitely going to have 3 different answers here. Okay, so what we're going to do in each case, rather than just start mindlessly trying to answer the question, let's determine the form in each case. Okay, in the first case, as x approaches 3, my numerator and denominator are both approaching 0, aren't they? In the next case, as x approaches infinity, the degree of the numerator is smaller than the degree of the denominator, is it? Now, technically, yes, it's still infinity over infinity form, but I can use degree perhaps. And in this case, as x approaches, well, let's see, my denominator is most definitely approaching 0, but my numerator is approaching negative 6. Oh, so let's see, if I'm approaching negative 3 from numbers bigger than negative 3, then x squared minus 9 would always be negative. And okay, yikes. I have 3 very different problems here, don't I? Very different. In the first case, where the indeterminate form 0 over 0, which means factor and cancel would be the right way to go. And in fact, I can factor and cancel on each of these if you choose. There would be nothing wrong with that. But in the first case, because the denominator here is x plus 3, x minus 3, this is going to be the limit of 1 over x plus 3. As x approaches 3, that limit is 1/6. In the second problem, I can multiply top and bottom by 1 over x squared, or I can simply use the degree argument. I'm going to use the degree argument. It's easier. The degree of the numerator is smaller than the degree of the denominator. So this is 0. And I'm going to put degree of numerator less than degree of denominator. In the third example, and by the way, if you did the factor and cancel, that would be fine. As I approach -3 from the right of -3, that means that the square of -3 would be smaller than 9, by the way. Or I should say the square of this of x would be smaller than 9, not the square of -3. So my denominator would be approaching 0 from the left. That means this is going to grow without bound positively. Yikes. I asked you the same function 3 times. We got a finite, we got an infinite, we got a 0. So this is why I pointed out before, the form is everything. Now, I don't necessarily need you to write this every time, but you probably need you to write this every time because the form dictated my strategy. This form meant I was going to factor and cancel. This form meant I only had to look at degree. I could have factored and canceled, but it wouldn't have made any difference. I still was looking at degree in the end. I will ask these types of questions on an exam, and often people forget to look at this. They'll factor and cancel, they'll do stuff, but they'll forget to look, what exactly are you taking the limit of in to get there? So now we've looked at infinite limits. Okay. In every conceivable way, you'll see an infinite limit. And again, vocab, transient terms. What are transient terms and how can I use them to my advantage? So now the last piece of the puzzle today, probably the simplest part, really, we're going to talk about something called continuity. And so sometimes it's easier to say what it isn't rather than what it is. So when we talk about continuity, I want you to think of, first of all, we're looking at a graph. Okay, it could be a piecewise function, but I'm thinking of a function in general. And so if I think of my function as a road, if I'm asking you the question, am I continuous at a particular place or not? Can I drive through it? If it's a road, can I drive through it? Or will there be an asymptote? Will there be a break in the graph? Will there be a hole there? Can I drive through the point? That means am I continuous at the point? So we first define continuity at a point. Okay, so we say that f of x is continuous at x equals c, c being a specific value, if and only if, some of you are familiar with this IFF, if and only if f of c exists, means c has to be in the domain. The limit as x approaches c of f of x exists. So the limit actually has to be there. And the third case, the limit as x approaches c of f of x must actually equal f of c. The last one seems kind of redundant, but we'll look at examples where all three of these potentially could fail. So the definition of continuity at a point is f of c exists. That means I can't have a removable discontinuity there, right? If I have a removable discontinuity, the limit will exist, but the functional value will not. In the last case, I can have a removable discontinuity and then fill it in somewhere else. So the function existed, the limit existed, but they weren't equal. So I want to do an example of each of these three pictorially. Okay, so in the first case, and I'm going to try to essentially draw the same function. So right now, let's say that's C, we'll say that's L. Okay, I'm asking, is this function continuous at x equals c? I think the answer would be yes. Okay, I can clearly drive right through that. So the first case is there's nothing weird going on. I'm continuous at x equals c. So this is graph number one. Now I'm going to do graph number two. Graph number two. I'm putting a hole there. So right now, the limit as x approaches c is in fact L. But f of c does not exist because there's a hole there. C is no longer in the domain. So I failed the first criteria. The limit existed, but I failed. F of c does not exist. F of c is not in the domain. So that's case number 2. Now I'm going to jump, or I'll say case number 3. F of c equals m. Now my function is defined at c. My limit definitely exists, but my limit does not equal my functional value. So I just failed the third criteria. Okay, so here's how you can fail the last one. This is defined for all real numbers. F of c exists, the limit exists, but they're not the same. Okay, that's probably the most obscure. All right. Now, that's the third criteria. Now, let me show you the fourth. There's only 4 possibilities. F of c exists, but the limit from the left is L. The limit from the right is M. So the limit does not exist. There's a clear break in my graph. Okay. So the way the second one would fail typically is something like this, like a break. The way the first one fails is usually a removable discontinuity. So the question of continuity is you say a function is continuous at every point that it's continuous. So when we talk about a function, we'll give it continuity over an interval. If I'm talking about a specific value, then you're pretty much comparing limits and things like that. So let's do an example. There's only really a couple of meaningful examples to look at in this case here. So let's consider the following function. F of x is x squared, let's say, plus 4x minus 12, and x squared minus 5x plus 6. Okay. I would like to know, where are the discontinuities and the type of discontinuities? So it turns out there's only a few types of discontinuities. So let me go back and talk about them again. We know the types of discontinuities. Okay. Removable. We're very familiar with removable discontinuity. If I gave you the graph y equals square root of x, we love this graph. It's a cool graph. Am I continuous at x equals 0? I'm defined at x equals 0. Am I continuous at x equals 0? Ooh, remember I said, think of continuity as there's a road. Can I drive through this point? Or am I going to hit a brick wall? You see, I'm defined at x equals 0, but I can't pass through it. There's nothing on the other side. And what we showed last week was the limit does not exist here because there's no left-hand limit. Oh, so I'm not defined at origin. That's called an endpoint. You cannot be continuous at the endpoint of a function because that's the end of the domain. There's nothing on the other side. Oops. Sorry, endpoint. Okay. So I'm not continuous where I have a removable discontinuity. I'm not continuous at an endpoint. In the previous picture, and whenever we have a piecewise function, we can always get something of this effect, where I have a break in the graph. Okay, that can only happen in a piecewise function, but I'm not continuous there because there's a break in the graph. Okay, and then the last one, maybe the coolest one of all. I have a vertical asymptote. I'm not continuous here at x equal 2. I'm not only not defined at x equal 2, I'm not continuous. In fact, whoa, right, there's a chasm there that I cannot cross. So the last one is called asymptotic. And that means specifically a vertical asymptote. So the 4 types of discontinuities: removable discontinuity, endpoint discontinuity, a break discontinuity, and an asymptotic discontinuity. All discontinuities are one of those 4. You don't need a graph, though, to determine them. It's actually kind of simple. Now, the break is probably going to be the most obscure, because the only way you're really going to get a break is if you have a piecewise function. This is not a piecewise function. Okay. Secondly, the endpoint is not as common because the endpoint means your domain must have an endpoint. Okay. So like the square root function, my domain is 0 to infinity, including 0, but then 0 would be the endpoint of the function. So I would have a discontinuity there. So now looking at this here, how am I going to figure out where the discontinuities are? Well, the first thing I would do is factor it. Okay, so my numerator is x plus 6, x minus 2. My denominator is x minus 3, x minus 2. Well, that makes it easy enough. Now, do we care where the numerator is 0? No, we only care where the denominator is 0. Where the numerator is 0 isn't the problem. The problem is where the denominator is 0. So where is the denominator 0 here? Well, let's see. I have x equals 3. I have x equals 2. But so wait, I can cancel these guys. You're right. I can remove x equal 2 from the problem as being an issue. I can remove x equal 2. So therefore, what kind of discontinuity is x equal 2? Come on.
Break.
Sorry, removable.
Removable. Yeah. Can't give that one away any easier, right? It's a removable discontinuity. What about x equal 3? Ooh.
Asymptotic.
Asymptotic, beautiful. Whatever remains after you cancel factors is going to be asymptotic. You're going to have a vertical asymptote. Okay, I'm going to put VA, vertical asymptote, or asymptotic. Now, here's the part that confuses people. What about x equal -6? No, the y value is 0. So that means I have the point -6, 0 on my graph. That's not a discontinuity. That's just where it crosses the x-axis. Oh, okay. So a common error is to figure out where the numerator is 0 and then treat that as part of the process. So I'm asking where the discontinuities are. All you had to do is factor it. Any factors that cancel, they're removable. Everything that's left in the denominator is asymptotic. And that's it. I can't make it any weirder. Not that one. So let's make a weird one. A weird one would be a piecewise one. So let's do a piecewise. Okay. I'll keep it simple. F of x equals, let's say it's f of x is x squared when x is less than -2. Let's say f of x is 6 when it's between 2 and 1, and yes, and it's x when it's greater than 1. This is a piecewise function. I do not need to draw a graph in order to answer this question. So I'm going to draw a graph anyway. There's no part of the answer that I need a graph, but sometimes it just makes it easier for us to understand what the heck's going on. So y equal x squared is a parabola, but this parabola doesn't start until about here. Okay. By the way, that's 4 units high. And, oh, you know what? I'm sorry. I just realized something. I want this to be, sorry, I want this to be a 1, not a 6. My bad. Can't 6. What was I thinking? Sorry, 1. So filling in the hole, and then open it this end. And it's y equal x forevermore. There we go. Okay, that's a fairly accurate graph. Now, again, I didn't need the graph to answer this. So if you were looking at this, first of all, what is the domain of this function? Be very careful. Is the domain all real numbers? Is a yes or no?
Except one.
All real numbers except one. So the domain is not the whole number line. It's all real numbers except for one. That's actually really, really important. That automatically means we have a discontinuity at one, doesn't it? Now, in general, do I have to go? Let me go through all the real numbers I can think of and see if it's continuous. Let's face it. Y equal x squared is continuous everywhere it's defined. Y equal 1 is continuous everywhere it's defined. Y equal x is continuous. These are nice, happy things. Nothing weird's going on. The only place that something weird could possibly go on is where I change definition. In other words, the values of -2 and 1 are the only possible places that anything interesting could be happening. Okay, because to the left of -2, I have a parabola. It's continuous forever. All polynomials, by the way, all polynomials are continuous everywhere they're defined. Okay, so that's not the issue. So we've decided we're going to check x equal 1 and x equal -2 and x equal 1. So let's start with x equal -2. The limit as x approaches -2 from the left of f of x is equal to the limit as x approaches -2 along the parabola. That does matter. And that limit would be 4. By the way, is the function defined at -2? Yes, it is. Right here, you know that. The function is defined at -2. So if my 3 criteria, the first criteria was met. F of -2 does exist. F of -2 is 1. Okay. Now let's do the limit from the right. That means I'm approaching it along this. Oh, it's the limit of 1. I have a horizontal line, and we know that the limit of a constant is the constant. So now the limit, and I'll write it formally. Like Nathan said, this is our summary. The limit as x approaches -2 from the left of f of x does not equal the limit as x approaches -2 from the right of f of x. Therefore, the limit as x approaches -2 of f of x does not exist. There is no limit as I approach -2. Therefore, what type of discontinuity could that be? What's the only type of discontinuity where the limit from the left and the limit from the right are different? And it's
Break.
not vertical asymptotes. It would be a break. So I'm simply going to write it's a break. Now, I know it's cheating that we have the picture, but it was a break because I got different limits. Okay. Now, remember, in the case where you have vertical asymptotes doing that, your left and right would be different, but they're also infinite. So it's asymptotic at that point. There's no asymptotes here, so that's not an issue. So now let's consider the limit for 1. So the limit as I approach 1 from the left of f of x, is equal to the limit as I approach 1 from the left. Now, from the left means I'm approaching it along the horizontal line, and that's just 1. The limit as x approaches 1 from the right of f of x. Now I'm approaching it along the line. So that's the limit as x approaches 1 from the right of x, and that's just 1. The limit from the left and the limit from the right are the same. Therefore, I can say that the limit as x approaches 1 of f of x is equal to 1. So does that sound continuous?
Professor, what's the 3 dots on where the break was? Sorry, if yeah, that. What's that
Therefore,
mean? Therefore.
yeah, it's a math. Actually, it's not just a math term. I think it's an English thing too, but math people like to use that because we're lazy. And I think it's because a lot of math people can't spell therefore. So I think that's part of it too.
Would it be similar to the equals or the any of the other notations that we recently used? Like, why would we want to use this over any of the other ones?
No, you got this, and this, therefore this. It's a logic thing. Anyway,
Okay.
so I've got the limit exists. So does that mean I'm continuous at 1? The limit existed. But what? F of 1 does not exist. That's the same as saying F is not defined at x equal 1. So the limit existed, the functional value didn't. So is it continuous there? No. What type of discontinuity? I mean, you know from the picture, but what type of discontinuity? The limit existed, but the functional value didn't. That means it's removable. And we got that by examining the limits, not from the graph itself. We just showed that the limit from the left and the limit from the right were both 1, so the limit existed. Now, here's a question I got for you guys. Is there anything I could do to, on either one of these discontinuities, is there anything I could do to the original statement of the problem that would make it continuous? Let's start with the easy one.
Shift our parabola.
Well, let's start with the easier of the two. How can I make this continuous? By making one of those two an or equal. Do you agree? If I made that or equal,
Yeah.
if I made that or equal, I'd be filling in the point. That's an easy one. So now going back the other way, you said shifting the parabola. Very specifically, what do I want to do?
Bring it
Shift
down
it
one
down.
unit.
So what would I want to do? I'd want to make it x squared.
Minus k.
Well, more specifically, x squared minus
1.
well, probably x squared minus 3, because they differ. These differ by 3 units. So if I have,
Oh,
so if I move this parabola down 3 units, then they would be joined. If I made one of these an or equal, then they would be joined. So I have the discontinuities because it's a piecewise function, but that does not mean that piecewise functions are always discontinuous. Be careful with that. Okay, so continuity is a huge thing as we move on, because basically from a calculus standpoint, a lot of things fail when a function is not continuous. There's a lot of conclusions I cannot make. So determining where something is continuous or not sometimes is the first step of a problem. I need to determine where it's continuous so I can move on. Now, when you're asking where's it continuous, you always start with, well, what's its domain? You see, anything not in the domain, I'm definitely not continuous at, because those functional values don't exist. Now, I used a term a moment ago. I said this function is not defined at 1. The term not defined simply means it's not in the domain. What does not defined sound a lot like mathematically? There's another word. Not defined and anybody?
undefined.
Undefined. Those sound really similar. They're not, in no way are they similar. And that throws people. The term undefined means you took a non-zero value and tried to divide it by 0. I'm talking about the slope of a vertical line. We say that's undefined. That's what undefined means. That's the only thing undefined means anywhere in mathematics. But when you say something is not defined there, that means it's not in the domain. So we'd used the square root function earlier, okay? The square root function, we're only talking real values here. So the square root function is not defined anything to the left of 0. It's not undefined. Now, are there times when not defined is undefined? The graph of y equals 1 over x is defined everywhere except 0. 0 is not in the domain, so the function's not defined at 0. Oh, by the way, what's happening at 0? I'd have 1 over 0, and that would be undefined. So there's the one time where not being defined produced undefined. But the term not defined only refers to, is it in the domain or not? It's nothing about the graph. Not defined means there's nothing there. Undefined means I have a vertical line. So it's kind of different things. All right, we will go ahead and stop there. Hold on.